have a parallelogram, and we're going to discuss a few properties about it. First off, if we have a diagonal, we know that the diagonal is congruent to itself. Also, we know that we have parallel sides because it is a parallelogram, which means alternate interior angles are congruent, and the left and right sides are also parallel. So we get more alternate interior angles, which are congruent. Therefore, we have basically just shown that the diagonal cuts the parallelogram into two congruent triangles. And you could do the same thing if you drew the other diagonal. So diagonals cut parallelograms into two congruent triangles. Since those triangles are congruent, their corresponding parts are congruent, so opposite sides of a parallelogram are congruent. The opposite angles are also corresponding, and you could do the same if you drew the other diagonal to get the other angles. So the opposite angles are congruent as well. And if we draw on that other diagonal, it's now cut into four congruent triangles, or four triangles, and they do have congruent, the triangles that are across from each other are going to be congruent, which you could show pretty easily just by stating that vertical angles are congruent. So we have the top and bottom triangle are congruent by angle, angle, side, which means corresponding parts are congruent, so this side would correspond with that side, and these two sides are also corresponding. So you could say that the diagonals cut each other in half, or the diagonals bisect each other. So there's a lot of special properties about parallelograms. You can also go on and talk about how rhombuses and rectangles and squares are parallelograms. So they're going to share a lot of the same properties, but have some unique properties of their own. So we have a chart that sums up all of these special properties. So for a parallelogram, like we just said, diagonals form congruent triangles. Opposite sides are congruent. Opposite angles are congruent. At least two opposite sides are congruent. The diagonals bisect each other. At least two consecutive supplementary angles. That's because they're parallel, so they'd be same side interior. Consecutive angles are supplementary. All of them are supplementary. And there's at least two congruent sides, because the opposite sides are congruent. So some of these are repetitive and take one pair or two pairs or whatever. The reason I have these three circled is because if you know both pairs of opposite sides are congruent, that's enough to prove that it's a parallelogram. Same thing with opposite angles. That's enough to prove it's a parallelogram. Or if the diagonals bisect each other, you can prove it's a parallelogram that way. So the ones with circles are if and only if statements that can be used either way. As I mentioned, rhombuses, rectangles, and squares are parallelograms, so anything that's true for a parallelogram will be true for those as well. there's special properties that each one has. For rhombus and square, part of the definition is all the sides are congruent, but also the diagonals of a rhombus bisect each other, or bisect vertical angles, or vertex angles, sorry, and the diagonals are also perpendicular to each other. A square is a rhombus because all the sides are congruent, so those three properties also apply to squares. And with rectangles, the diagonals are congruent. There's at least one right angle, there's actually four. And it has at least two consecutive congruent angles. Since they're all 90, they're all congruent. And since a square is also a rectangle because it has four right angles, those are true for squares as well. A trapezoid only has at least two consecutive supplementary angles because the top and the bottom are parallel, so these two angles will be supplementary because they are same side interior, which would obviously be true if it's an isosceles trapezoid as well. But since it's isosceles, it has at least two congruent sides. It also has at least two consecutive congruent angles, the base angles. And actually, the angles up at the top as well. The diagonals are congruent, and at least two opposite sides are congruent, since it's isosceles. So let's try to apply some of those properties. We have a parallelogram with the midpoints marked. So the big shape is a parallelogram. We are being asked to prove that if you connect the midpoints, you get another parallelogram. So in order to prove that a shape is a parallelogram, we either need opposite sides congruent, opposite angles congruent, or to show that the diagonals bisect each other. So looking at this, since we know ABCD is a parallelogram, opposite angles are congruent. So we get these triangles that are formed are congruent by side angle side, which would lead to these opposite sides of the inner figure being congruent because they are corresponding parts. Same thing with the bottom left and the upper right triangles. They are congruent by side angle side, which means EH and FG are congruent because they are corresponding parts. But that shows that opposite sides are congruent, which means EFGH is a parallelogram because opposite sides are congruent. For our next example, we're told that a rhombus has diagonals of lengths 6 and 8. So we'll say this one has a length of 6, this one has a length of 8. Go back to our check sheet. The diagonals of a rhombus, because it is a parallelogram, the diagonals bisect each other. So since they bisect each other, if this diagonal is 6, that means both parts are 3. Yeah, the diagonal is 8, which means each part has a length of 4. Also, since it's a rhombus, the diagonals are perpendicular. So these are all right triangles. And since it's a right triangle, we can use the Pythagorean theorem. 3 squared plus 4 squared equals 25, so this side must be 5. All of them are 5. So find the length of the sides, that would just be 5 centimeters.